Good morning, students. In the previous class, we have seen about open circuit PN junction and the formation of the PN junction. So, if we consider the open circuit PN junction, here we have the P-type material and here we have N-type material. Okay, in between we have what the depletion region. So here this electric field that is present in developed in depletion region can be indicated graphically here. This is the negative charge. The charge that is present in this depletion region is negative charge up to this point, up to the junction at x equal to 0. And here we have plus is there, that is nothing but the positive charge. So this conjunction, this positive and negative charge gives the electric field for us. And that variation of electric field I am indicating like this. Okay, so this is what how you can represent an open circuit PN junction charge and electric field graphically. Okay, now we'll go with the biased PN junction. That means PN junction diode is biased. Then what happened? And what are the types of biasing techniques we have for a PN junction? Okay, so the thing we are going to see here in this class. Okay, so here biasing of a PN junction diode. Then what is biasing is nothing but applying an external voltages to a device is called as what applying external DC voltages to a semiconductor device is called as what biasing. But here biasing of a PN junction diode is nothing but connecting a PN junction to an external DC voltage source is called as biasing. Okay, so what is biasing of a PN junction diode? Here is nothing but connecting a PN junction to an external DC voltage source is called as biasing. We have two types of biasing. One is forward biasing of a PN junction, and another thing is reverse bias. Forward bias and reverse bias. Okay, so first we will consider the PN junction diode is a forward bias. Okay, that means in the previous section we have seen the open circuit. That means we are not connecting any external voltage, and if we observe the characteristics, that becomes open circuit PN junction diode characteristics. But here we have two types of biasing we have, that is first one is forward bias and second one is reverse bias. Okay, so PN junction diode forward bias, when we call this PN junction diode is forward bias, and when we call the PN junction diode is in reverse bias. And if it is a forward bias, what happened to the hole and electron concentration or the movement of holes and electrons in the P and N type materials we have to see, and we will draw the characteristics of that forward bias. And next second one is what the reverse bias condition. Okay, what is the reverse bias and how we can verify the characteristics of the PN junction diode for a reverse bias case. Okay, now first we will consider the PN junction diode forward bias. When we call this one as PN junction diode is a forward bias. So this, if suppose I consider this is the PN junction what that is formed and that is open circuited. Now what happened in PN junction diode is forward bias means when we connect a battery to the PN junction diode such that the positive terminal of the battery is connected to the P side and negative terminal to the N side, then that PN junction is said to be in a forward bias. So what is the statement here? A PN junction diode is connected to a battery such that the positive terminal of the battery is connected to the P-type material and negative terminal of the battery is connected to the N-type material. Then that type of biasing is called as forward biasing of a PN junction diode. Okay, if I do that one, previously what we have here, we have the holes, white color circles or white colors is holes that are majority carriers, and electrons here in N-type that are majority carriers, holes are the minority carriers. So here if you observe here 8 holes is there in P-type, but only 2 electrons will be there. That means what majority carriers are holes and these 2 are the minority carriers that are electrons. Similarly here also we have in N-type material that is majority carriers or electrons. Okay, so this one I am connecting to a battery such that when a positive terminal is connected to the p-type and negative terminal is connected to the n-type, then the type of connection is called as then the type of biasing is called as, for a p-n junction diode, it is forward bias. Okay, then what happened if I do that thing, what happened here? So for a small applied voltage, here it is plus is there, and this potential, this barrier potential, here what we have, that is depletion region potential or space charge potential, what we have here electric field is minus to plus here we have, but here we are applying the battery as plus to minus and minus to plus, like that. That means here we are applying the voltage, external voltage or battery or DC voltage, that is the direction opposite to that of electric field that is present in the depletion region. Okay, so because of that, there is a less effect we have previously. If we consider the open circuit condition, the resistance will be more in the depletion region for the movement of holes and electrons from p-type to n-type and n-type to p-type. But if you apply some external bias or external voltage, what happened, that is opposite direction to the electric potential or electric field that is present in the depletion region. So if you observe here, plus is connected to the p-type, that means minus will be there in the electric field in the depletion region. Minus will be present are connected to the n-type material, but plus will be there in the electric. Both are. So here the applied electric field or applied voltage is opposite to the direction of the depletion region electric field. So there is a possibility of decreasing in the depletion region, or the resistance will be decreased as we apply or as we connected in the forward bias. So here what happened is, if we connect or if we increases this voltage, external voltage, what happened, positive terminal is connected to the p-type and negative terminal is connected to the n-type. So positive and positive polarity of holes will be repel. Okay, so here the positive terminal is connected to the holes, therefore there is a repulsive forces between the positive terminal and the holes, and here the electrons, that is the negative terminal and the electrons, so both are the same polarity, so they will repel. That means what, the positive, due to this positive terminal that is connected to the p-type, the holes will repel due to this positive terminal, and they will move towards the junction. That is, they are trying to move towards the junction, and at the same time here the electrons, they will repel with the negative terminal of the battery, and they will also move towards the junction. Okay, so like this, here what happened, if I increase further forward bias, so if I increase more forward bias, what happened is, there is a movement of holes from p-type to n-type and n-type to p-type, and if I increases further, they will get more energy, repulsive force. Due to that, they travel or they penetrate into the depletion region, and the depletion region will be reduced. Okay, so that is what the process that is taking place in p-n junction diode as a forward bias. Okay, so here we have that, and I have the complete operation of the depletion or space charge region in a p-n junction, which acts as a barrier for majority carriers to cross the junction. That means what, here we have majority carriers p-type and n-type. Initially, without applying any bias, external bias, what happened is it offers, the depletion region will offers more resistance. More resistance means they cannot allow the majority carriers, that are holes that are present in p-type, to cross the junction and goes into the n-type. Similarly, the depletion region will resist or will oppose the electrons to move from n-type to p-type by crossing the junction. So this is what we can say, that here the depletion region, the electric field that is present in the depletion region opposes the movement of charge carriers from p-type to n-type and n-type to p-type. That's what here I have given. The depletion or space charge region in a p-n junction, which acts as a barrier for majority carriers to cross the junction. Okay, then when the p-n junction is forward biased, the holes are repelled from the position positive terminal of the battery. So the holes will be repelled uh, by the positive terminal of the battery, and they will move into towards the junction. Similarly, the electrons will repel from the negative terminal of the battery, and they will move towards the junction. That's what I explained now. Okay, so electrons from n-type region across the junction and enters into the p-type region. Due to the attractive forces that is generated in the p region, the electrons are attracted and moves towards the positive terminal. Okay, so here what we have here, we have what n-type material we have. Okay, these n-type electrons, that is majority carriers, will attract it. So due to the negative terminal, they will repel and they will come across the junction, and at the same time there is attractive forces of positive terminal will be there. They will attract and the electrons will move into the p-type material or p region. Similarly here, we have, due to this positive terminal, the holes will repel and they will attracted by the negative terminal. Therefore the holes will move into the n-type material. Okay, like that there is a movement of holes and electrons will takes place. Simultaneously the holes are attracted to the negative terminal of the battery. By the movement of electrons and holes, the current will flows. So therefore because of attractive forces of holes by the negative terminal, and because of attractive force of positive terminal, that is attracts that attracts the electrons from n-type to p-type. So there is a possibility of movement of electrons from p-type to n-type, that is movement of holes from p-type to n-type and electrons from n-type to p-type. Okay, so this is the process. So there is a movement of charge carriers, automatically the current flow will be there. So this is about the forward bias. As I increases more and more voltage, what happened is, when we apply external bias, the holes and electrons acquired energy. Some of the holes and free electrons penetrate the depletion region. This reduces the potential barrier or width of the depletion region or barrier height. As a result of this, more majority carriers diffuse across the junction. Okay, it is no problem. But here, as the increasing in the voltage, positive terminal, they will repel and they will cross the junction and they will move into the n-type. But these holes, some of the holes will be recombined with electron, and negative and positive charge will becomes zero. Okay, that means the electron and holes will be vanished here. Some of the holes that are crossing the junction, they will recombine with the electrons that are present in n-type, and at the same time some of the electron that crosses the junction due to repulsive forces, so they will recombine with the holes that are present in the p-type. So because of recombination, already we have studied about generation and recombination. Because of recombination, what happened is, the whole electron pair will disappear. Okay, so therefore the concentration of holes and electrons will be reduced, but it will be compensated. Okay, so you can observe the statement here. These carriers recombine and cause movement of charge carriers in the space charge region. For each recombination of free electron and hole that occurs, an electron from negative terminal of the battery enters into the n-type material. If then drift towards the junction. So what happened, we have seen here, due to the recombination, the electrons in the n-type and holes in the p-type, that means electron hole pair will be disappear. So to compensate that, the electrons will be supplied from this negative terminal. Suppose one electron is gone at this point due to recombination, the corresponding electron is replaced from the negative terminal. At the same time, the nearer to this positive terminal, the p-type, one electron will be released due to this forces, and that electron release means automatically there will be a space will be empty space will be present. That empty space we will consider as a hole. So therefore, because of recombination, there is a loss of there is a disappearance of whole electrons, that is whole electron pairs, but they will be compensated by using the negative terminal and the positive terminals. Okay, so that is the point. we have. Okay, so these carriers recombine and cause the movement of charge carriers in the space charge region. For each recombination of free electron and hole that occur, an electron from negative terminal of the battery. So whatever the electron that is missing, that can be replaced with the negative terminal of the battery and enters into the n-type material, and that process is called as what? The drift towards the junction. Okay, you can observe here what I explained. The holes are moving like this and the electrons are moving like this. Okay, and they will cross each other at a particular point. What happened is there is some recombination takes place, that due to that recombination the whole electron pair will be disappear, that can be replaced with the electrons from the negative terminal. These electrons will move into the n-type. At the same time the hole will be created because one electron will be free due to the forces, repulsive forces. Okay, so this is what how we can have the operation in the p-type material. Near the positive terminal of the battery, an electron breaks a covalent bond in crystal and enters into the positive terminal of the battery. For each electron that breaks its bond, a hole is created. That's what I told. This hole drift towards the junction. Okay, towards the junction. This is how the missing or the disappear or electron and holes due to the recombination can be replaced with this negative terminal, and at the same time breaking of covalent bonds nearer to the p-type material or positive terminal, that gives one empty space. Okay, so this is what how you can replace the or how you can compensate. So if I increases further and further, what happened is the repulsive forces that are coming from the positive terminal and negative terminal will overcome the resistance of the opposition forces that offer for the holes and electrons to cross the p-type to n-type and n-type to p-type, that is junction. Okay, so here to overcome that, the as we increases the bias more and more, what happened is they can overcome the repulsive forces, will overcome the depletion region, and the depletion region width will be reduced. With depletion width will be reduced. You can observe here, as I increase more and more external voltage, previously here we have this much of depletion region we have and more electric field we have, but as I increases this electric field, that is external bias, what happened here, the depletion region width will be decreased, and there is no depletion region if you observe. Therefore the holes will move from p-type to n-type, and the electrons will move from n-type to p-type freely, because the opposing force is not there, that is vanished or that is reduced. The depletion region is reduced. In the first point itself, I told that the depletion region is the main resistance or that is opposing force for the electrons and holes that are moving from n to p and p to n respectively. But as we are increasing more and more value of the external bias, what happened, the depletion region will reduce, and the holes and electrons can move freely from p-type to n-type and n-type to p-type. Therefore there is more amount of current will flows as the more number of holes and electrons crosses the junction from p-type to n-type and n-type to p-type. So that is the point. So at a particular point, what we call up to a particular point, there is no movement of holes and electrons. That means crossing of holes from p-type to n-type or n-type to p-type cannot take place. And at the starting point, the voltage will try to compensate, try to overcome the depletion region potential. So at the starting point, there is no current flow. There is a small amount of current flow that will be negligible. But as we increases the voltage, external bias, what happened is the depletion region width will be reduced, and the electron and holes will move freely from P to N and N to P. Okay, so this is the diagram where after if you increases the more amount of external voltage, the depletion region will be zero, width will be zero. That means it is reduced. So the holes will freely move into the n-type, and electrons will move freely from n-type to p-type. Okay, so that's what here the final step that will happen. Okay, so in p-type material, neither then the current in the p-type material is due to movement of holes. The current in the n-type material is also due to the movement of electrons. The current continues as long as the battery in the circuit. Okay, as long as if you connect the battery, so the current flows from p-type to n-type. That is, in the p-type, the holes are moving from p-type to n-type, so the direction of current is from p to n. But the electrons are moving from n-type to p-type, but here the current direction due to the electrons is nothing but opposite to the direction of the electrons. So here the direction of current due to electrons is from p to n, and at the same time the whole current is from p to n. So in this p-n junction diode, in the forward bias, the current will flows from p to n, p region to n region. Okay, so that is the point we can observe. This current will continuously flows until we disconnect the battery. Okay, so here we have one basic definition. The amount of energy required by the electron and holes for crossing the junction is equal to the barrier potential, that is nothing but 0.3 volts for germanium and 0.7 volts for silicon and 1.2 volt for gallium arsenide. So this is what how we can have a p-n junction diode is in a forward bias. Okay, so now we will see the VI characteristics of that p-n junction diode. If the external voltage is applied on the silicon diode is less than 0.7, the silicon diode allows only a small current, and that is negligible. Okay, because what happened is if you apply a small voltage here, only that voltage is try to compensate, try to overcome the depletion region, but it cannot completely reduces the depletion region. So because of that, there is some repulsive force, there is some opposing force for the electrons and holes that are crossing the junction. So there is a less number of electrons and holes will move from n-type to p-type and p-type to n-type if we apply a lesser voltage. If suppose if you consider a silicon diode, if that voltage, that external voltage is less than 0.7 volts, what happened is there is no current will flow, that is small amount of current will flow, that will be negligible. Okay, once when the external voltage is applied to the silicon diode reaches above the reaches the 0.7 volts, then the junction diode starts allowing the large electric current. At this point what happened is if it reaches, if the external voltage reaches the 0.7 volts, what happened is the depletion region completely reduced. Depletion region width will be completely reduced, and therefore the electrons and holes will freely move from n-type to p-type and p-type to n-type. Because of that, there is a large amount of current will flows in the p-n junction. Okay, from p to n. Okay, so that is the point what we have here. We are going to discuss about a very important definition, that is cut-in voltage. The forward voltage at which the silicon diode starts allowing a large electric current is called cut-in voltage. So where the in the forward voltage at which the silicon diode starts flowing large electric current is called as cut-in voltage. The cut-in voltage for silicon is 0.7, and for germanium in the bracket I have indicated that is 0.3 volts. Okay, so in the forward direction, in the forward bias, if I consider VF is on that is forward voltage on x-axis, and corresponding current is on y-axis, and it is that current will be flow is nothing but in terms of milliamperes. Okay, so that is what we have. IF is on y-axis and VF is on x-axis. That is, for a given forward voltage, what is the current, we have to draw the graph. Okay, so here if you observe at this point, I am indicating if I take the silicon at this point, the VF is equal to 0.7 volts. Here if you observe, before that there is a small amount of current is there. After reaching 0.7, suddenly the current will increases. That means what, at that point the depletion region width will be reduced to 0 for ideal case. Okay, so therefore we will consider at 0.7 volts for a silicon, there is a large amount of current will flows in the PN junction diode forward direction from P to N. Okay, for a germanium, what is the cut-in voltage here? 0.3 volts. 0.3 volts. The forward voltage at which the silicon diode starts allowing the large electric current is called as what? Cut-in voltage. Okay, that cut-in voltage is 0.7 volts for silicon and 0.3 volts for germanium. Okay, so this is for the VI characteristics of PN junction in forward bias. Okay, right. Next we will go with the PN junction diode reverse bias case. Okay, so what is the forward bias means? If the positive terminal of the battery is connected to the p-type semiconductor and the negative terminal is connected to the n-type semiconductor, then that type of biasing for PN junction diode is called as forward bias. Okay, but here we have the exact opposite one, that is PN junction diode at reverse bias case. Okay, PN junction diode at reverse. If the negative terminal of the battery is connected to the p-type semiconductor and positive terminal of the battery is connected to the n-type semiconductor, then that diode is said to be in a reverse bias. Okay, then the diode is said to be in reverse bias condition. Okay, so here if you observe this one, previously what we considered a open circuit to PN junction diode, when it is connected negative to the p-type material. Here p-type material is this one and n-type material is this one. When we call the PN junction diode is in reverse bias, when negative is connected to the p-type and positive is connected to the n-type, then that type of connection we call as what? Reverse bias connection for a PN junction diode. Okay, so now what happened here? So if I apply negative terminal to the p-type material, what happened here? Here the holes are majority carriers and that are positive. Okay, so there is attractive forces that are coming from this negative terminal for the holes, and at the same time what happened is these electrons that are present in n-type are attracted towards the positive terminal. Okay, attractive towards the positive terminal, leaving whatever the ions we have. N-type consists of positive donor atom and p-type consists of negative acceptor atoms. By leaving them, the holes will be attracted towards the negative terminal, and here the electrons will be attracted towards the positive terminal, and the remaining whatever the donor ions we have here, that will be as it is. They are immobile ions. They will be present there itself, and here also acceptor atoms we have. So because of this reverse bias, the electrons will be attracted towards the positive terminal by leaving the immobile ions there, and at the same time the negative terminal attracts the positive holes. Therefore, because of that, there is an accumulation of negative and positive charge. Not accumulation, but there is a presence of, there is an increasing of negative and positive ions across the junction will increases. So you can observe here clearly the diagram. Previously, if I consider this reverse bias, just reverse bias, what happened here? It will be like this. If I increases the reverse bias voltage, small voltage, so what happened? These holes will be attracted. These holes will be attracted. Here we have the p-type semiconductor. These holes will be attracted like this, and here the electrons will be attracted to the positive charge. So what happened here? Negative ions and positive ions. Previously a small region is there, depletion region, but here what happened here, as I increases the negative reverse bias voltage, so what happened is this depletion region increases. So if the depletion region increases, the opposing force for the majority carriers to move from p-type to n-type and n-type to p-type will be increases. Okay, therefore there is no movement of majority carriers from p-type to n-type and n-type to p-type. So therefore there is no current flow due to majority carriers in the PN junction diode reverse bias condition. Okay, so that's what we have. I have written here. If the external reverse voltage is applied on the PN junction diode, is increased, the free electrons from n-type semiconductor and holes from p-type semiconductors are moved away from the p-n junction. So actually the junction is here, they will move away from the p-n junction because of attractive forces of holes by the positive negative terminal, electrons by the positive terminal attractive forces. The majority carriers move away from the p-n junction, so only the immobile ions will be there. So due to that immobile ions, the depletion region width will be increases. So you can observe clearly, I have differentiated here. This is at the starting point. As I increases the reverse bias voltage, so they will attract towards the attractive terminals. The holes will be attracted towards the negative terminal, and the electrons will be attracted that are present in n-type towards the positive terminal. Due to that, the depletion region will be increased. From the p-type, here again I am seeing reading this one. If the external reverse bias is voltage is applied on the p-n junction diode is increased, the free electrons from the n-type semiconductor, that is majority electrons, and the holes from the p-type semiconductor are moved away from the p-n junction. This increases the width of the depletion region. Previously only the small width will be there. As I increases the reverse bias, external reverse bias voltage, what happened, that width becomes double, the depletion region width becomes double from this point to this point. That means more immobile ions will be present. So that offers more development of the electric field. So that is the opposing field for the holes that are moving from p-type to n-type, and electrons that are moving from n-type to p-type, that is majority carriers. Okay, right. So the wide depletion region of reverse biased p-n junction diode completely blocks the majority charge carriers current. So it can, because of more amount of depletion region or electric field, they cannot it cannot allow the majority carriers from p to n and n to p, that is holes from p to n, and electrons from n to p. That means there is no movement of majority carriers from p to n and n to p. That the higher depletion region will blocks that movement of holes and electrons that are majority carriers. Therefore there is no current will flows, that is majority carrier current, but a small amount of current will flows, that is nothing but minority charge carrier current. Okay, so that minority charge carriers means here we have in n-type, what are the minority charge carriers? Holes is the minority charge carriers. In p-type, what are the minority charge carriers? That are electrons. These are very less number because of this positive terminal that repels the holes that are minority carriers present in n-type towards the junction, and at the same time because of this negative terminal, the electrons that are minority carriers that are present in p-type will be repelled and they will cross the junction. So due to that, there is movement of minority carriers that are electrons from p-type to n-type, and at the same time holes from n-type to p-type, there is a small current will flow. That current is called as reverse saturation current. Okay, reverse current. Okay, so that's what the point. However, it allows the minority charge carrier concentration. Here n-type minority charge carriers are holes. These will be repelled and they will move across the junction, and they will cross the junction and move into the p-type. Similarly, electrons are the minority carriers here, and they can also move from p-type to n-type because of repulsive forces of the negative terminal. Okay, so you can observe the free electrons in the p-type semiconductor, that is minority carriers in the p-type semiconductor, and the holes are the minority carriers in the n-type semiconductor carry the electric current. Okay, only the minority carrier current will flows in the reverse bias condition. That electric current which is carried by minority charge carriers in the p-n junction diode is called as what? Reverse current or reverse saturation current. Okay, in the n-type and p-type semiconductor, very small number of minority charge carriers is present. Hence, a small voltage is applied on the diode, pushes all the minority carriers towards the junction. So the positive terminal that repel the holes that are present in the n-type material, and the holes will crosses the junction and they move into the p-type material. Similarly, the electrons will move. Okay, so that is the point, that current is called as reverse saturation current. Okay, So in other words, in the reverse bias, the voltage are the point at which the electric current reaches its maximum level, and further increases in reverse bias voltage does not increases the electric current is called as what? Reverse saturation current. So even though if you increases further more and more reverse bias voltage, there is no change in the reverse saturation current, because uh, only some minority holes and electrons will be there. They will cross the junction, and no more minority carrier concentrations will be there in n-type and p-type. So uh, there is no dependency of this reverse saturation current on the electric, that is external voltage. That is the point. The reverse saturation current is depends on only temperature, because if the temperature increases, there is a generation of minority charge carriers increases. That means what? If the temperature increases, whole electron pair will be generated in p-type and n-type. That means the electrons that are generated in p-type material will be considered as minority carriers, and the holes that are generated in n-type semiconductor will be, that is minority carriers. So as we increases, so here the reverse saturation current cannot depend on the external reverse bias voltage. It only depends on the temperature. As the temperature increases, why it depends on temperature means, as the temperature increases, there is a generation of minority charge carriers. That is, whole electron pair generation is taking place in both the p-type and n-type materials. Due to that, the minority charge carrier concentration will increases. Therefore, if the minority carrier concentration increases, means automatically minority current will be increases, or reverse saturation current will increases. By conclusion here, the reverse saturation current is depends only on the temperature. It cannot depends on uh, the applied external bias. Okay, so if we further increases the reverse voltage, there is a possibility of junction breakdown. Okay, if the applied voltage on the diode is increased continuously, the PN junction diode reaches to a state where the junction breakdown occurs and the reverse current increases rapidly. Okay, we will see how it will be, the increase in the current. So this is the VI characteristics of a PN junction in reverse bias condition. This one. So at the starting point, there is some reverse saturation current will flow due to minority carriers. As I increases the voltage, that is reverse voltage. Here positive, in forward bias we have taken the forward voltage, and in reverse bias we are considering that one as the reverse voltage. So as we increases the reverse voltage at the starting point, up to this point, what happened? There is a small current will flows. Okay, that current is nothing but reverse saturation current. At this point, what happened? If we increases further and further continuously the reverse bias voltage, the junction breakdown will happen. Okay, so that will raises the current that is flowing through the diode will raises sharply, that like that. Here, if you observe, up to this point, it is maintaining a small current due to minority carriers. Okay, but after, if you increase further reverse bias voltage, what happened at this point? Suddenly, the reverse saturation current increases sharply, and it will be maximum. This causes the junction breakdown. So that's why it is called as breakdown voltage. So this is the reverse characteristics of a diode. Okay, in germanium diode, a small increase in temperature generates a large number of minority charge carriers. I already told this one. As the temperature increases, the valency electrons uh, are lightly bounded with the attractive forces of the nucleus. Because of that, for a small change in the energy, or for a small change in the that is what temperature, automatically those valency electrons will gain some energy, and they come out of the valence cell and they will become free. That's why in germanium diodes, a small increase in temperature generates large number of minority charge carriers. The number of minority charge carriers generated in the germanium diode is greater than the silicon diode. Hence, the reverse saturation current in germanium diode is greater than the silicon diodes. Okay, what is the conclusion here? Uh, the reverse saturation current in germanium diode is greater than the silicon diode due to only one reason, because because of less attractive forces that offers on the valence electrons of the germanium as compared with the silicon. Okay, so that is what we have here. And the complete combinedly the p-n junction diode VI characteristics I have provided here. So after this here up to this 0.3 volts for germanium and 0.7 volts for silicon, there is a small amount of negligible amount of current is flows in the forward direction. If it reaches its cut-in voltage, that is 0.3 volts for germanium and 0.7 volts for silicon, the in the forward bias condition, the depletion region will reduces and the current will rises sharply, rapidly. That means more current will flows from P to N, that is from P type to N type materials. Okay, so here this is nothing but the complete characteristics of the p-n junction diode. If you observe this one, here the forward bias voltage is taken on x-axis, positive x-axis, and negative x-axis is reverse voltage. On y-axis, positive y-axis, I have considered the forward current in milliamperes, and in the reverse direction, reverse current will be taken on negative y-axis, and it is considered as microamperes. So forward current will be measured in milliamperes, and reverse current will be considered as in microamperes because it is very less current, that is minority charge current. Okay, reverse saturation current. So if you observe this one at this point where the current, more current starts flowing in the forward bias condition, that voltage is called as what? Knee voltage. That is 0.3 volts for germanium, 0.7 volts for silicon. So this is the VI characteristics of the p-n junction diode, both in forward direction and forward bias and reverse bias. Okay, so that is the point. Now we have p-n junction diode. A p-n junction diode is one of the simplest semiconductor device around, and which has the characteristics of passing current in only one direction. P-n junction diode is two-terminal device that are anode and cathode, and the direction of the current is from P to N in p-n junction forward bias. Okay, so this is p-n junction is simple device, a semiconductor device, which consists of p-type material and n-type material. So here p-type is nothing but majority carriers or holes, n-type is nothing but majority or electrons. So I will consider that anode or the positive terminal is this side, and cathode I am taking this side. Okay, so this indicates here we have p-type material and n-type material, and this is p-n junction representation, and this is nothing but schematic symbol. We can use this one in the circuits, that is that consists of both two terminals, that is anode terminal and cathode terminal. This is the symbol of the diode. The diode symbol is what? This one, a triangle and a line. Okay, so here if you observe this a real component, if you find the diode in the lab, so the lab in the lab the diode will be a complete black. We have black body will have, on that one we can have a silver coated circle. Okay, so in real if you see in the lab the diode structure will be like this itself. So the black color, and on that black color completely a silver coating is will be there, circle will be there. So here whatever that silver coating circle we will consider as negative terminal or cathode terminal, and the remaining opposite side we will consider as a positive terminal. So this is the representation of p-n junction, and this one is the symbol of p-n junction that consists of anode and cathode terminal. And at the same time, in real component identification, that will be it seems like this only. So it consists of complete black color body, and on that one a silver color is placed in a round circle. So that round circle side we will consider as a cathode, that is negative terminal, and the opposite one will consider as a positive terminal. So the diode symbol will be anode and cathode, that is plus and minus. Okay, so this is what we can have forward bias. In reverse bias we will consider the polarities as minus and plus. Okay, so now what are the applications of p-n junction diode? P-n junction can be used as a rectifier. In the next chapter itself we are going to study the rectifier. One of the very important application of p-n junction diode can be used as a rectifier. Next one, used as a signal diodes in communication receivers. So in the second semester you are going to learn in analog communication, that is envelope detector is used for amplitude modulation detection. Okay, so that is another application, and it is used as a varactor diode in a radio and TV receivers. In this chapter, in the second chapter itself, we are going to study this varactor diode also. Diode can be used as a switcher. That means in the forward bias, there is a current flows from P type to N. More amount of current will flow. That means current flow is there, means if the switch is on, the current will flow. Generally, what we have observed in our home, the switch is on, the current will flows. But a diode can also be used as a switch, on switch and off switch. And the diode is in forward bias, the more current will flows, that considered as on switch. And in reverse bias condition, there is negligible current will flows, that is considered as off switch. And that's another important one is this diode can be used as a Zener diode in stabilizing circuits. Okay, that we can see in the next topics. Okay, so this is about the biasing of PN junction diode, forward bias and reverse bias, and forward bias characteristics and reverse bias characteristics, and what is the cut-in voltage and what is the knee voltage, and all those things we have discussed in this class. And what is the symbolic representation, and what is the schematic representation of PN junction diode, and how you can identify a real PN junction diode if you see in the lab. Okay, so and the applications of PN junction diode we have seen. So for today I am stopping.